Hi, my name's Jonathan. I've got a three-phase motor which I want to run from a single-phase supply. It's the coolant pump motor for my pillar drill or drill press, and it's a three-wire motor marked 415 volts three-phase, but my supply is 240 volts single-phase. The main motor of the drill was relatively straightforward to run using a variable frequency drive or VFD to provide a 240 volts three-phase supply and changing the motor winding configuration from star to delta by rearranging the way the motor's 6 wires connect to the supply. Ideally, I do exactly the same thing with the pump motor, but this is a 3-wire motor, hardwired to run in a star configuration, so it doesn't have a terminal box where 6 wires can be rearranged to run in delta. So the first half of this video covers converting the 415 volts 3-phase 3-wire star motor so it can be powered using a VFD to provide 240 volts 3-phase and the motor windings reconfigured to run in delta. As you will see, the motor ran using this setup and would run for up to 15 minutes, and then the VFD would shut down displaying an error code, usually drive overload or motor overload. So the second half covers trying to find out what the problem is, determining the cause and finding out what can be done to prevent it, or could have been done to prevent it. Having started with a 3-phase pump, that's now been taken apart, the ends of the motors taken off. And this is a piece of interest. It's only got 3 wires coming out, so it can't easily be switched from star to delta. But I'm going to see if I can find the star point. The star point being where the 3 other ends of the windings are joined together. I'm assuming the star point is amongst all these wires tied up on the end of the stator. Here we've got one of 3 connections where the relatively inflexible end of a winding, a single core, is twisted and soldered onto a much more flexible cable that can be taken out to an external connector. Besides 3 of those joins, I then found a connection where 3 wires were joined together. 2 wires, and there's a 3rd coming out just down here. So that's possibly the star point. Well, there's some solder here anyway, so it's definitely a join. Not much I can do here. These 3 wires joined together at the ends of the 3 windings, winding finishes, whilst the 3 black flexible leads are joined to the other ends of the windings, the winding starts. The plan is to bring all 6 out to a terminal box similar to that already seen mounted on the main motor. Right. Now the matching ends of the 3 windings can be found along with the resistance of each winding. That one and that one are 26 ohms, that one and that one are 26 ohms, and there's another pair of 26 ohms, so it's the same resistance. So yes, it looks like they're pairs. That's what I was looking for. The heat shrink used here has an operating temperature of 125 degrees Celsius. Acrylic coated woven glass sleeving, which has a rating of 155 degrees, would have been a safer choice. With hindsight, I should have picked one colour for the flexible extensions I added to the disconnected star point winding ends, also known as the winding finishes, and another colour for the extensions to the other 3 wires, which are the winding starts. I should also have added some cable identification showing the matching start and finish of each winding. As it was, I extended the 3 winding ends from the star point and replaced the existing winding start extensions, all 6 using red sheathed flexible cable and black heat shrink. I then tied the 6 wires back down to the coils to make them secure using woven glass fibre tape, making sure they exited at the cutout. The 6 wires out have been broken up to star point, giving 3 windings with 2 ends each, giving 6 wires. Used resistance measurements to find which 2 were either end of a coil. Bought this block, which is the standard star delta configuration block. Put it all together without knowing which winding is U, V or W. The block is marked U, V or W and has U1, U2, V1, V2, W1, W2 to join the coils together correctly. But whether it was the correct coils I was joining together, or in fact the coils were the right way around, if there is a right way around, I didn't know. So I put it all together and in a bigger box to mount on here to contain the connection, the configuration block. This is the old one and that's too small as well. So for now, for testing, it's going to have to live like this. This is the kit I'm using to test. BMC filter, inverter, control switches, emergency stop button, 3-phase output, 13 amp input. At first go, the important point here is that there are 6 wires coming out the motor now, and a configuration block can be used to set it up in delta. Oh, you can't see it. It works. Whether it's going the right way is another matter. There is an arrow on the top of the housing. Which is pointing in this direction. I'll slow it down to check. Yes, it's going in the right direction. Well, that's 50 Hertz. I'm very pleased with that. I can see from my diary for that time that I was getting drive overload or motor overload errors on the VFD, and that I tried altering the motor rated current parameter and motor no load current parameter, but it looks like the values I was assigning them were much too high. About 20 possible causes are given in the VFD manual for motor overload and drive overload, and whilst I adjusted some of the parameter values linked to these errors being triggered, I only had partial success, and eventually I put the motor and drive aside until I had time to take another look at it. This time, instead of focusing on the drive and its software generated errors and parameter values, I started by looking at the current flowing on the three phases between the drive and the motor. When building a control circuit for a single phase 11 amp motor, I put in overload protection to prevent damage to the motor. This took the form of an overload relay to activate the off switch if overcurrent, i.e. any current over 11 amps, which given time would damage the motor, was detected. This allowed me to set different current levels and work slowly up to 11 amps and slightly above when I realised there was something wrong, and eventually detected a capacitor that needed replacing and seized, which together went switching from the start circuit to the run circuit and would have damaged the motor in time. 0.5. The 0.5 is half an amp. Putting in similar protection for this motor would have been a very good idea. Half an amp is actually the rating on the motor plate. Compared to yesterday, 1 minute 52, not very long at all. OL1. 1.6 amps there. And on the black phase, one amp. .8. 1.08 rather amps in the black phase. One minute this time. So the question is what to do next. Got a motor that runs now and again if it's not too hot, under no load, with this drive, with one phase looking decidedly dodgy. But it fits, the brackets and so on, and it's the original part, which I'd like to keep if I can. I then noticed that the current I measured at the VFD on one phase didn't necessarily match the 0 amps current I measured on that same colour phase at the motor. Brown. This seems weird. And my phase is switched over in the connector. Well, the colours certainly don't match up. We've got grey to brown, black to black, and then brown to grey. Wouldn't it help if you use the same naming convention? Instead we've got 4 different ones. We go from U/T through RGB, I think, on one side of the connector, to L1s, L2s and L3s on the other, and then to U's, V's and W's at the other end. The varying currents on the phases were worrying, so I stripped the motor down and found that some, but not all, of the coils that make up the windings were blackened and burnt. So I contacted a motor rewind firm who said they could rewind it, the stator. I wanted to check the whole thing first. So I reassembled everything, checked it was still working, made up a crate to ship it in, weighed it so I could book a carrier pickup, and sent it off for rewinding. The rewind company sent me a report back saying it had overheated, damaged the insulation, which I knew, and the impeller was worn, and quoted the price for a new replacement pump they could supply. I turned down this offer and received the pump and motor back in pieces. I was all ready to give up on this motor. Then a friend of mine who I'd been talking it over with rang me one morning to say he'd been thinking about it overnight and suggested some tests I might carry out. So I thought, well, if he's taken the trouble to think about it, I feel obliged to carry out the tests he suggests. So I thought I'd better start by checking whether the damage to the windings would invalidate the results of any testing by checking winding resistance and winding insulation resistance. On W, W2 26.2. So after labelling each wire, I disconnected them all and checked the insulation resistance of each winding using my Mega 1711 multifunction tester set to measure mega ohms at 500 volts. We'll go around them as they're coming out. W2. $290 or thereabouts, mega ohms, and V2. Test 270 mega ohms. With winding resistance and insulation resistance seeming to be okay, that meant I could proceed with diagnosing the actual cause of failure of the motor. So I set up to test, as in this circuit, with a AC input to one coil. That AC input voltage of about 10 or 20 volts is provided by a variable transformer, or variac, which takes its 240 volts input from the mains, but via an isolation transformer to reduce the risk to me if I should touch something I shouldn't. So I can put an AC voltage through one coil, join the other two coils together, and hopefully deduce something from the result. And got zero output. This indicates that, contrary to the naming shown on the board, the link is between two starts and the voltmeter is across the two finishes, which could be 7 volts each and thus nothing between them, or vice versa, and the meter is across the two 0 points, and again there's nothing between them. So change the links, for which 23 volts in, I got 14 volts out. So I took this to mean that the link is across dissimilar ends of the windings. By that I mean a start and a finish, so that you've got one voltage, perhaps 0 volts at V2, 7 at V1, then another 0 at W1 and a 7 at W2. So when you stack the one on the other, you get 14, which is what I measured. I read somewhere that doing this, you could expect about 40% of the voltage on the input coil. Well, I put 23 volts in, and with 14 out, that gives 7 across each coil, which is 30%, which I'm willing to accept. So now I put in a voltage, not across the U's, but across the V's. And instead of measuring there, and I put the link. So I put in a link from what was my W1 to the U2 and measured the output voltage between U1 and W2 and got an output voltage. And as the text with the procedure said, if you get an output voltage, you've connected a 1 to a 2 in your connection. But my first test where I got a voltage said, no, this isn't a 1 and that's not a 2, they're the wrong way around. So going by that, I've actually connected a 2 to a 2. but I've got a voltage, so that doesn't make sense. This test says my old naming convention, a 1 to a 2, is fine, but the previous test said my 1 to a 2 was wrong. So they don't match up, so I don't know where I'm going wrong. So as a compass had arrived, I decided to go with a simpler test where one winding at a time was tested, rather than try and work out what was going on from a test that involved 3 windings. Right, I've got 10 volts through U1 positive, U2 negative. So getting that in position, turn the power on. Seems to be south is there. I started off talking about the compass pointing to north or indicating south was in a certain direction, but actually the compass is aligning itself along the magnetic flux, which is represented by the lines here and the direction. I also should have mentioned that this is a DC voltage I'm putting through the U winding to see what it does in the way of poles. Now it's pointing north over there. So north, right, is there. And presumably if I reverse U1 and U2, we'll get the opposite. Well, we've got south pointing this way now. North has now moved to here. So I did this for U, V and W windings, marking on the paper underneath the motor where I found the poles. Seems to be in the wrong place. If it's meant to be 120 degrees out, it's expected to be over here. Well, I'm going to mark, this is with them reversed, and so I'm going to mark the reversed. Which is here. So this is where the motor was, or is. Right, so I'll just move this out the way. So it seemed to have one there, V2, the V's reversed, one there which is the U's, and the W there. That's negative to V1, or rather to what I took to be V1 when I originally wired the motor up. Because I wired it up positive to V1. So I actually had this. So is that how I've wired it up? No wonder it's got a bit blackened, when I should have wired it up like that. So that's positive to U1 and negative to U2. And so we're at 4 o'clock. Right, positive is on V2, negative is on V1. Go the right way. Right, power on. So I think it should be at 12 o'clock, but actually it's at 6 o'clock. To W2, positive to W1. And you can see now that we're at 4 o'clock. or at minus 120 degrees. Well, that was simple to do once I'd worked out what needed doing. I mean, this motor's had it now, but I just want to prove, or try and prove, why I got it wrong. Because I think I reversed the V1 and the V2 start and finish. I want to do more than one test if I can. This is the compass test. The next test will involve zero-centered galvanometer. Right, I'm set up to do the Finding Polarity of Induction Motor Method 2 by DC. As given in this printout. By adjusting the zoom as I've just done, I missed out the upper part of the galvanometer. You can just see the base of the needle in the video, and based on that and my commentary, I've recreated it using graphics. I choose one of the phase windings. Now these instructions refer to A, B and C as the windings. Well, I'm going to refer to them as U, V and W respectively. Randomly choose one of the phase winding terminals, say U1 and U2. Positive terminal of the battery to U1. So positive terminal of my power supply in this case is to U1. And the negative is to my switch. And from there to U2. So that's one side of the circuit. The other part is the galvanometer. The meter is connected across one of the other two phase windings, say B phase randomly. So I'm going to choose V. So I've got the meter positive going to V2, and I've got the meter negative going to V1, as I've called them. Whether that's correct naming, we'll see. At the instance of closing the switch, observe the deflection of the meter pointer. Power supply on, press the switch, and we've got a negative deflection. But there isn't a positive. There isn't a clockwise deflection. So that's saying if it had been a clockwise deflection, this would have been V2. But it's not a clockwise deflection. My naming of the V, start and finish, are reversed. So I'm now going to go on to the W phase, following the procedure to identify other terminals, W1 and W2. So moving on to the next page. The positive terminal of the DC to U1 and the negative terminal of the DC to U2 through the switch. Got it. If there is a positive or clockwise deflection, then the terminal connected to the positive of the meter is W2. This is the positive of the meter, and it's going to the one, don't get them mixed up, and it's going to there, and the negative is going to W1. So if you get a positive deflection, the terminal connected to the positive of the meter is W2, i.e. my naming is correct. If we get a positive deflection. So we'll press a terminal and we do get a positive deflection. So by this, and assuming my first phase naming is correct, or relative to my first phase naming, I've got my second phase, the V, misnamed, i.e. I've mixed up V1 and V2, which is what I thought already from the pole tests using the compass. So that would seem to be some verification that, yes, I've got the V's, the phase reversed, the V phase reversed, i.e. V1 and V2 are misnamed. At the time this didn't make sense, but on reflection I assumed it was the W coil that I'd misnamed, and I think actually it was the V coil, in which case this result would make sense. I would have a W1 to a U2, a 1 to a 2. So to round up, I modified a 415 volts, 3-phase, 3-lead motor, hardwired in star, to bring 6 leads out to allow it to be reconfigured to run in delta and powered by a 240 volts, 3-phase output variable frequency drive. This modified motor ran unloaded, sounding quite smooth, but the VFD would cut out after running for anything up to 15 minutes, reporting either drive overload or motor overload. At this point I wasted time focusing on the drive settings. It was only when I measured the phase currents that I discovered the motor was unbalanced, drawing excess current on 2 phases. This was confirmed as the cause of overheated windings, but didn't explain why the motor was drawing that excess current on the 2 out of 3 phases. 3 different tests using 1 a compass, 2 AC input and a voltmeter, and 3 DC input and a galvanometer all indicated I'd mixed up the start and finish of the V winding and reversed the V phase as covered by Robert Rosenberg in his electric motor repair book. I originally knew which were the winding starts, the 3 leads brought out of the motor, and which were the winding finishes, they were the 3 soldered together. But for various reasons I lost that identity, which performing any of the tests done later at that time would have identified. I've put some links below to some of the references I found useful and hope this has been of interest, and thanks for watching.